There is a number that should not exist, negative 270 degrees Celsius. Not on some remote exoplanet, not in a laboratory vault buried under a mountain, but in the space between the stars, the same space that cradles more suns than there are grains of sand on every beach on Earth. This is the paradox intelligence agencies studying deep space physics have had to reckon with for over half a century. An ocean of starlight, and yet a cold so. Total, it makes Antarctica's worst winter feel like a warm afternoon. Vostok Station, Antarctica, July 21st, 1983. Deep inside the frozen heart of the East Antarctic Plateau, a thermometer records minus 89.2 degrees Celsius, the coldest temperature ever measured on the surface of planet Earth, confirmed by the World Meteorological Organization, and still the official record today. Human skin freezes solid in under a minute at that temperature. Diesel turns to jelly. Steel turns brittle enough to shatter like glass. It is, by every human measure, the outer edge of what a body can survive. And it is nowhere close to the coldest place we know about. Because deep space, the space that fills the 93 billion light-year-wide observable universe, the space between here and the Andromeda Galaxy, the space that separates every one of the roughly 200 billion trillion stars, scientists estimate exist in the observable universe, sits at an average temperature of 2.7 Kelvin, that is minus 270.4 degrees Celsius, just under 3 degrees above absolute zero, the theoretical floor beneath which nothing in the universe can ever get colder. Antarctica's most brutal recorded night is nearly 180 degrees warmer than the average temperature of the universe around us. This is where the mystery begins, because it should not work this way. Stand near a bonfire and you feel heat radiating onto your skin. Stand near 100 bonfires and the heat multiplies. So stand inside a universe containing an estimated 1 septillion stars, a number so large that if you tried to count them one per second, it would take longer than the current age of the universe several times over. And logic says you should be standing inside an oven, not a freezer. Every star is a nuclear furnace. Our own sun alone radiates about 384.6 septillion watts of energy in every direction, every second, according to NASA's own solar physics data. Multiply that number by the vast population of stars scattered across every galaxy in the observable universe, and the raw energy output becomes almost impossible to comprehend. And yet, space itself, the medium those stars are burning inside of, remains locked at a temperature just a hair above the absolute physical limit of cold. Something is happening to all that heat. Something is swallowing it, diluting it, erasing it before it can ever accumulate into warmth. And the answer to where it goes, and why the coldest place documented in the entire universe isn't even the empty space between galaxies, but a dying star's exhaled breath just 5,000 light years from where you're sitting right now, is stranger and colder than almost anyone expects. To understand why billions of suns can burn across the cosmos and still leave the space around them frozen solid, you first have to understand something that sounds almost too simple to be true. In space, there is, in the strictest physical sense, often nothing there to actually get cold. Temperature, as physicists define it, is not some ambient quality that fills a room like a fog. Temperature is a measurement of how fast particles are moving and colliding with each other. It requires particles. It requires matter. A crowded room full of people bumping into each other generates heat through friction and motion. An empty room generates none because there's nothing there to move. Now stretch that empty room out across trillions of cubic light years, remove the walls, the floor, the air, and you start to understand the first piece of the puzzle. Most of the universe isn't cold in the way Antarctica is cold. Most of the universe has almost no there at all. Interstellar space, the space between star systems, contains on average less than 1 atom per cubic centimeter. For comparison, the air you're breathing right now contains roughly 10 quintillion molecules in that same tiny volume. Deep space is not just cold, it is close to the emptiest environment scientifically confirmed to exist, and that emptiness is the first key to unraveling why an ocean of starlight fails to warm the ocean of nothing surrounding it. But emptiness alone doesn't explain everything. There is still radiation, pure light and heat energy traveling silently across the void from every star, unblocked, unobstructed, moving at the speed of light in every direction, forever. So why doesn't that radiation add up? Why doesn't the accumulated heat of a septillion suns eventually turn the void into something warmer than a Californian summer? The answer sits at the intersection of two forces most people have never had to think about: distance and a law of physics so unforgiving it governs everything from your phone's Wi-Fi signal to the light of the most distant galaxy ever photographed. And once you understand that law, you'll understand why NASA's own spacecraft, vehicles built by the smartest engineers on the planet, machines sitting directly in the same sunlight that scorches Earth's surface, still have to fight every single day against the encroaching absolute cold of the space they travel through. Here is the law that breaks the illusion, the inverse square law. It is one of the oldest, most tested principles in physics, and it explains almost single-handedly why a universe stuffed with stars can still be one of the coldest environments science has ever measured. The inverse square law states that as energy, light, heat, radiation spreads outward from a source, its intensity doesn't decline gently, it collapses. Double the distance from a light source and the energy reaching you isn't cut in half, it's cut to a quarter. Triple the distance and the intensity falls to 1/9. Move 10 times farther away and you receive only 1/100th of the original energy. Energy doesn't travel through space in a straight beam that stays intense forever. It spreads outward in an expanding sphere, like ripples fading across the surface of an endless pond, growing thinner and thinner the farther they travel from the point where they began. Now, apply that law to the actual scale of the universe. The nearest star system to our own sun, Alpha Centauri, sits roughly 4.24 light years away, a distance so vast that light itself, moving at 209,792 kilometers every single second, takes over 4 years just to cross it. And Alpha Centauri is, relatively speaking, our next-door neighbor. Most stars in our galaxy sit dozens, hundreds, or thousands of light years apart from their nearest neighbors. Stretch that across the roughly 93 billion light-year diameter of the observable universe, and you begin to see the second half of the answer. The stars aren't actually close together at all. They are almost unfathomably isolated from one another, sprinkled across a canvas so enormous that their combined heat, by the time it reaches any given patch of empty space, has been diluted by distance into something almost undetectable. This is confirmed, not theorized. Spacecraft sent beyond Earth's protective magnetic field and atmosphere have measured it directly. NASA's own solar physics data shows that even in our own solar neighborhood, a region flooded with far more direct starlight than most of the universe will ever experience, because we orbit an actual star. Space just outside Earth's atmosphere averages only about 10 degrees Celsius when you account for both the heating and cooling effects of passing in and out of sunlight. That's a comfortable spring day, and it's already the exception, not the rule, because Earth sits unusually close to an active, energetic star. Move even modestly farther out into the vast tracts of interstellar space between star systems, and that average temperature collapses toward the 2.7 Kelvin baseline of the universe at large. But there's a third piece to this puzzle, and it's the one engineers designing spacecraft and spacesuits have had to solve with brute mechanical ingenuity, because it turns out space isn't uniformly cold at all. It's catastrophically, violently uneven. On the International Space Station, orbiting roughly 400 kilometers above Earth, astronauts conducting spacewalks are documented by NASA to experience temperature swings between approximately positive 121 degrees Celsius in direct, unfiltered sunlight and negative 157 degrees Celsius the moment the station passes into Earth's shadow, a swing of nearly 280 degrees, sometimes within a single 90-minute orbit. That's because without an atmosphere to circulate and average out heat the way air does on Earth's surface, temperature in space becomes purely a function of whether you are facing a source of radiation or facing away from one. There is no wind to spread warmth. There is no ocean current to buffer the temperature. There is only light, hitting a surface directly, or the absence of it, plunging that same surface into cold within moments. This is precisely why spacesuits are engineered less like winter coats and more like miniature spacecraft. NASA's extravehicular mobility units use multiple insulating layers of aluminized mylar to reflect away incoming radiation on the sunlit side, while trapping the astronaut's own body heat against the punishing cold of the shaded side, sometimes needing active cooling systems more than heating systems, because a working astronaut's body generates so much heat with nowhere for it to escape in a vacuum that overheating, not freezing, becomes the more immediate danger. So the picture starts to sharpen. Billions of stars exist, yes, furiously burning, radiating unimaginable quantities of energy every second. But the universe surrounding them is so overwhelmingly empty, and the distances between those stars so catastrophically vast that by the time starlight reaches most of the space in the cosmos, it has been diluted by the inverse square law into something too faint to register as meaningful warmth. Combine that with a vacuum that has no medium to conduct or convect heat the way Earth's atmosphere does, and you get a universe where light exists in abundance, but heat, real, measurable heat, remains one of the rarest resources in existence. But this still leaves one thread unresolved. If starlight fades and radiation is rare, what actually sets the 2.7 Kelvin floor that every patch of empty space seems to share? Why does even the darkest, most starless region of intergalactic space still register a temperature at all, rather than true absolute zero? The answer to that question takes us back nearly 13.8 billion years, to the birth of the universe itself, and to a discovery that would eventually earn a Nobel Prize for two scientists who, at first, thought their instrument was simply broken. In 1965, at Bell Labs in Siedlungshaus, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were calibrating an antenna designed for satellite communication when they picked up a strange, persistent hum of microwave static. It came from every direction, at every hour, regardless of where they pointed the receiver. They cleaned the equipment. They chased away a pair of pigeons that had nested inside the antenna. The static never went away, because the static wasn't a malfunction. It was the oldest light in the universe, reaching them from every direction at once. That signal is now known as the cosmic microwave background, the residual afterglow of the Big Bang itself, confirmed by NASA's COBE satellite mission in 1989, and refined by later missions including WMAP and ES's Planck telescope. Roughly 380,000 years after the universe began, matter cooled enough for electrons and protons to combine into stable atoms for the first time, and in that instant, the universe, which had been an opaque, blindingly hot plasma, suddenly became transparent. Light that had been trapped, scattering endlessly off free-floating particles, was released to travel freely in every direction, and it has been traveling ever since. Over nearly 14 billion years as the universe expanded, that ancient light stretched and cooled along with it, dropping from a blistering 3,000 Kelvin at the moment of its release down to just 2.725 Kelvin today, a figure measured with extraordinary precision by ESA's Planck Space Telescope and confirmed as one of the most exact numbers in all of modern cosmology. This is the true floor of cosmic temperature. It is why deep space, even in regions containing no stars, no planets, and no visible matter whatsoever, still registers a temperature rather than absolute nothing. The cosmic microwave background bathes literally every point in the observable universe in this faint thermal glow. The last true fingerprint of the Big Bang, still detectable in every direction you point a sensitive enough instrument, including, right now, in the static between certain untuned television channels. But here is where the story takes its strangest turn. Because if 2.7 Kelvin were truly the coldest temperature the universe could produce, that would be remarkable enough. Except scientists have confirmed something colder, something that, according to NASA's Jet Propulsion Laboratory, defies the very background radiation that fills the rest of the cosmos. 5,000 light-years away, in the constellation Centaurus, a dying star is exhaling its final breath. It's called the Boomerang Nebula, and in 1995, astronomers Raghvendra Sahai and Lars Åke Niemann, observing it with a submillimeter telescope in Chile, measured its outer gas at approximately 1 Kelvin, minus 272 degrees Celsius. That is barely 1 degree above absolute zero itself. And remarkably, it is colder than the cosmic microwave background radiation that fills the rest of the universe. It is, as confirmed by NASA, JPL, the only object discovered so far that is colder than the afterglow of the Big Bang, a natural refrigerator so efficient it is actually absorbing background radiation from the rest of the cosmos, rather than emitting its own heat. The mechanism is almost as strange as the result. The dying star at its center is expelling gas outward at roughly 500,000 kilometers per hour, and that violent rapid expansion causes the gas to cool far faster than gas, expanding at ordinary speeds. The same principle that makes the gas from an aerosol can feel cold against your skin, playing out on a stellar scale. If your mind is already trying to process the idea of a place colder than the birth of the universe itself, make sure you're subscribed. Because what we uncover in the back half of this investigation, how this cosmic cold actively threatens human spaceflight and what it reveals about the search for life itself, is where the story becomes truly unsettling. So now the full picture assembles itself. Antarctica's Vostok station at minus 89.2 degrees Celsius remains the coldest temperature ever officially recorded on Earth's surface, though NASA satellite data reanalyzed in 2013 identified pockets on the East Antarctic Plateau near the ridge between Dome Argus and Dome Fuji that may have reached minus 93.2 degrees Celsius in August 2010, a reading researchers at the National Snow and Ice Data Center described as approaching the physical limit of how cold Earth's surface can possibly get under clear skies and calm air. That's already a temperature most humans would not survive more than a few minutes exposed to. And yet the cosmic microwave background that fills the space above every square inch of our planet sits at 2.7 Kelvin, nearly 180 degrees colder still. And beyond even that, tucked inside the dying breath of a single distant star, sits a pocket of the universe measured at just 1 Kelvin, 3 times colder than the coldest point ever confirmed on the surface of our world. Cold, then, is not a single number stretching evenly across the cosmos. It is a landscape, one shaped by radiation, distance, motion, and the leftover fingerprint of creation itself. And understanding that landscape isn't just an academic curiosity. It is, right now, one of the central engineering challenges standing between humanity and its future beyond Earth. Every spacecraft ever launched beyond Earth's atmosphere has had to be built as a direct answer to this cosmic cold and to the violent temperature swings that come with it. NASA's own engineering documentation on thermal control systems confirms that without active regulation, the sunlit Io side of the International Space Station would soar to 250 degrees Fahrenheit, while its shaded side would simultaneously plunge to minus 250 degrees Fahrenheit, a difference so extreme that, in the words of NASA's own Science Mission Directorate, there might be a comfortable spot somewhere between the two, but finding it wouldn't be practical, let alone survivable, for long. Instead, the station relies on multi-layer insulation blankets, ammonia coolant loops, and external radiator panels working continuously around the clock, just to keep the interior at a livable 22 to 24 degrees Celsius for future missions to the moon's permanently shadowed polar craters, where temperatures are expected to plunge as low as minus 230 degrees Celsius, or to Mars, where nighttime cold regularly drops far below anything experienced on Earth's surface. This isn't a peripheral engineering detail, it is the central design constraint. Every layer of insulation, every coolant loop, every choice of reflective material on a spacecraft's hull exists because the cold of space is not gentle, distant, or theoretical. It is immediate, extreme, and, without engineering intervention, lethal within minutes. And this cosmic cold carries implications far beyond engineering. It shapes where scientists believe life could plausibly exist at all. The reason astrobiologists focus so intensely on the narrow band of distance around a star known as the habitable zone isn't arbitrary. It's a direct consequence of the same inverse square, law that dilutes starlight into near-nothingness at interstellar distances. Move a planet too far from its star, and the diluted warmth simply isn't enough to sustain liquid water. Move it too close, and the opposite extreme takes over. Earth exists in the razor-thin margin where the inverse square. Dilution of our sun's energy happens to land at precisely the temperature where water remains liquid, where chemistry can become biology, where cold does not win outright. That, perhaps, is the most sobering realization to come out of this entire investigation. Our warmth, the very warmth that allows any of us to exist to ask this question in the first place, is not the universe's natural state. It is a rare, fragile exception, carved out of a cosmos that defaults overwhelmingly to cold. Every star may be a furnace, but furnaces separated by trillions of kilometers of near-perfect vacuum do almost nothing to warm the space between them. The default setting of the universe, confirmed by NASA, by ESA, by Nobel Prize-winning measurements of the cosmic microwave background, is a razor-thin margin above absolute zero. Warmth, life-sustaining warmth, is the anomaly. Cold is the rule. So the next time you look up at a clear night sky and see it scattered with what looks like countless stars, remember what that view is actually showing you. Not warmth, not comfort. What you're looking at is a thin, scattered handful of furnaces, isolated across distances so vast that their heat dies long before it ever reaches you, set against a backdrop of near-absolute cold that has remained essentially unchanged for nearly 14 billion years, ever since the universe's first light was set free to travel forever through the dark. Antarctica's ice will always be counted among the harshest environments a human being can survive. But it is, in truth, nothing more than a distant pale echo of the cold that waits just beyond our atmosphere, a cold that begins roughly 2.7 degrees above the absolute limit of physics, and that, in at least one dying star's final breath, somehow finds a way to become colder still. We are not warmed by the universe. We are, for a brief and improbable moment, sheltered from it. And that shelter is the rarest condition the cosmos has to offer.